Welcome to example number 4. We have the vector addition of forces. Shown in the problem, we have 3 point charges with their amount of charge listed and the distance that separates each of these charges from charge 1. We're asked to find the magnitude and the direction of the total force of these two charges exerting on Q1. The first thing we would do in this type of problem, as we did in the previous example, is you sketch the situation, which has already been shown for you. The next thing we want to do is to draw a free body diagram on this charge, Q1. Remember that opposite charges attract and likes repel. So if we look at along Q2 and Q1, we can see that's a negative charge, and this is a positive charge. And we know when the charges are unlike or opposite, they attract. So there would be a force of 1 on 2 pulling it down along this axis, or there would be a force of 2 on 1 pulling it up along that axis. And we're only concerned with the force on Q1. So we're only going to show the forces acting on that. So this arrow represents the force of 2 on 1. Similarly, we see Q3 and Q1 have attractive forces as well, because this is negative and this is positive. And so we'll have a force of 3 on 1 pointing right along this axis. So this is F3 on 1. Okay, so we are looking for the vector addition of these two forces to find the resultant force on Q1. What we need to do now is use Coulomb's law to find the magnitudes of these two forces. So using Coulomb's law, we have force of 2 on 1, which is equal to K times the absolute value of Q1 and Q2, and divided by the distance between them, R12 squared. And substituting, we get the following. There's Coulomb's constant. Here you'll notice that I've changed both the microcoulombs to coulombs. Remember that 1 microcoulomb is equal to 1 times 10 to the power negative 6 coulombs. And then we have the distance in meters, and it's squared. And using your calculator, the force of 2 on 1 will be equal to 9.59 newtons, approximately. I would suggest that you store all of this answer into your calculator because you'll use it later. Next, let's find the force of 3 on 1, which gives you the following expression. And substituting, you get this. And then on your calculator, the force of 3 on 1 will be equal to 17.98 newtons. Now we know the forces, the magnitude of these two forces. We now need to take these forces and break them up into components. And I just realized probably at this point would be a good idea to show my coordinate system right on Q1. And there's my coordinate system. There's my x-axis. I put right along that force 3, 1, and the y-axis here. And so hopefully you'll see that the force 2 on 1 is neither along the x or the y-axis, so I'm going to need to break that up into components. So we need to add up all the components. I like to do it nice and neatly in the table, so I would suggest that you construct a table at this point where you can show all of your addition of the x and y components. So in the first column, I'm going to call that the force for all the forces I'm going to be adding up. The next column is where my x components will go, and the next column is where I'm going to put all my y components. So we have only two forces that we need to add vectorially. We have the force of 2 on 1, and we also have the force of 3 on 1. Let's start with the easiest force. You can see force 3 on 1 is right along the x-axis. That means it has an x component of 17.98, and it has no y component because none of it is along the y-axis, so we're just going to put 0 there. Next, we have force 2 on 1. We need to break that up into components. We see there's a 73-degree angle with respect to the x-axis. To make this a little easier, in case you've forgotten this, I'm going to draw a triangle showing the x and y components for force 2 on 1. So I've redrawn force 2 on 1 right over here, and I want to get the x and y components. And constructing a parallelogram, and there is force, the x component of that, and this is the y component of that force. But I'll move that force over here And we have here, let me label this. This is the force. We'll just call this force 2 here now instead of force 2 on 1. Here we'll write this as force 2x for the x component, and here's force 2y for the y component, and this is an angle of 73 degrees. Now we need to develop a trig ratio to find each of these F2x and F2y. You'll see that for the x component we want to use this side because we know it, that's 9.5 newtons, and we want to try to find the x component. And hopefully you realize the cosine of 73 degrees is the adjacent, which is F2x, that x component, divided by the hypotenuse F2. So the x component of that force is going to be F2, which is 9.5 newtons, times the cosine of 73 degrees. And then similarly, if we want to find F2y, we're going to use sine of 73 degrees is equal to F2y divided by the resultant F2. And so F2y will be equal to 9.59 newtons times sine of 73 degrees. So let's input that over here. The x component is 9.59 times the cosine of 73. And then we have over for the y component 9.59 times the sine of 73. And I like to add all the signs on here, like the pluses and minuses. Remember that in this quadrant, any forces going in here, both the x and y components will be positive. So here this is positive and this is positive. And this force is going to the right, and so that's positive, and 0 we don't have a sign for. So be careful with the signs, because if you have any forces going over here or here, then you have negatives to deal with. And make sure your calculator is also in degree mode as you go through this problem. Next, we need to find the total x and y components. So we're going to use your calculator. Hopefully you saved these numbers into your calculator, stored them, and pull out your calculator and add these to find the total x component. So 9.59 cos 73 plus 17.98 will give you 20.8 newtons. And 9.59 sine 73 will give you 17.2 newtons approximately. And both of these are positive, which means that the x component is to the right here and the y component is up here. So this resultant is going to be somewhere in this quadrant here. So now we need to find the total force by forming these components together, and we're going to use Pythagorean theorem. Remember that the fx squared, that's this one right here, plus fy squared, and we're going to take the square root of that sum. So substituting in, we get the following. And I've just realized this doesn't make sense. 9.59 sine 73 is not 17.2. Let's recalculate that. That should be actually 9.17 newtons here. And then here we'll put 9.17 newtons. And then re-inputting this into my calculator, I'll get an answer of 22.7 newtons. Next, we need to find the angle, and hopefully you remember tan theta will be equal to the y component divided by the x component. And substituting, you'll get the following, which gives you an angle of 23.8 degrees with respect to the x-axis. So at this point you could write a statement about the resultant force. The resultant force has a magnitude of 22.7 newtons and is directed at 23.8 degrees above the positive x-axis. And there's your resultant force 1 at an angle of 4 degrees. You'll notice that we were fortunate in that this force was right along the x-axis and we didn't have to break this up into components, and we were also fortunate in that when we broke up this force, both of them were along this quadrant. Be careful when you have situations, say if this was a positive force, then this force 3 on 1 would be to the left. Or if this was a positive force, then this force 2 on 1 would be down here in this quadrant, and you'd find actually both the x and the y components would be both negative. Okay, and that's it for this problem.